So welcome to this talk about initiating lane and bound formation in heterogeneous pedestrian dynamics. So my name is Antoine Tordeux. I'm from the University of Wuppertal, and this is a joint work with Basma Kelfa and Raphael Korbmacher, who are both PhD candidates at the University of Wuppertal, and Andreas Schneider, who is physics researcher at the University of Cologne. So the topic is about, generally speaking, collective behaviors in pedestrian dynamics. And so interestingly, many types of collective behaviors occur in pedestrian dynamics. This can be, for example, lane formation for counterflow, that is observed here into an experiment done in Jülich. This can be also strip, bound, or chevron formation for crossing flow. We have also stop-and-go waves. So unidirectional pedestrian flow describes stop-and-go waves. This is also a phenomenon that is observed in road traffic flow. Another example here is intermittent flow at a bottleneck with also pedestrian moving in different direction. Theoretically, these collective behaviors rely on nonlinear effects, nonlinear interaction of the agents here, and a fast transition from a disorder state to another one, showing pattern structures, organization, like here this lane or so the traffic waves here propagating upstream. And theoretically, so the model are also nonlinear and can describe metastability. So several stable state coexist. So this is so the collective behavior results from the behavior of the agents. And this is related to motility-induced fast separation or motility-induced fast transition in the active physics, active matters in statistical physics. So I have here selected a bar of review articles about the topic. And what is interesting is to try to understand which kind of microscopic behaviors of the agents follow the emergence of collective dynamics here at a macroscopic scale, and often it's not trivial to deduce from the behavior of the agent the collective dynamics that will self-organize. So in this contribution, so we try to explain and understand so lane and bound formation in unidirectional flow according to different models of heterogeneity. So we consider that so we have an agent on the plane moving according to a given model. So for example, the social force model from Dirk Helbing that describes, so according to the states, local states of the systems, for example, the distances to the neighbors and some parameters, P, for example, the maximal speed, the agent side, and other parameters of the model. So it will describe the motion, so the acceleration rate or the speed, if it is a speed-based model. And we'll consider two species systems, so two different types of agents, 1 and 2, with different settings also for the parameters, P1 and P2. And we have two models, two heterogeneity model. For the first one, it is a static or quenched heterogeneity model. We attribute statically, the two parameters settings, P1 and P2, to the two agents types. So this is for the agent type 1, we have the parameter P1, and for the agent type 2, we have the parameter P2. So this corresponds to heterogeneity of the characteristics of the agent when we consider, for example, mixed flow, including pedestrian and bicycles, for instance. And we can assume that the desired speed of a pedestrian is smaller than the desired speed of a bicycle. The size is also different. So we have statically different characteristic for the agents. So this is the first heterogeneity model. For the second one, we consider now that we have an heterogeneity into the interactions. And this is now a dynamic mechanism. We consider that the value of the parameter are P1 when the agent is interacting with an agent having the same type. when the agent interacts with another agent, so this means when the agent, the closest agent in front have a different type, then the parameters will be P2. In such a case, we aim to model so heterogeneity in the interactions, saying that, for example, a pedestrian reduce or change his behavior when he or she interacts with a bicycle. Maybe he will reduce a little bit the desired speed, and this is the same for the bicycles that can, when he or she interacts with a pedestrian, he will reduce the speed or increase the time gap, for example. So we have two heterogeneity mechanisms here. In the first one, it is a statically heterogeneity model. According to the agent type, we have different setting of the parameters. In the second one, it is a dynamic heterogeneity model. Here, the value of the parameters depends on the type of the agent in front. And according to this type, if it is the same or if it is different, the value of the parameters will be changed. So we have here an illustration, one dimension of the two heterogeneity model. So in the first one, so we have two types of agents, circles and triangles, and two values for the parameters, P1 and P2. For the first model, so the triangles have the value P1 and the circles the value P2. And this is always like this, so the statically quenched heterogeneity mechanisms. For the second one, we have the value of the parameters depend on the type of interaction. This triangle has in front another triangle, so the parameters are orange, let's say a high desired speed. This one interacts with a circle, the triangle interacts with a circle, he or she has a reduced value of the parameters, so the value P2. And both of them here interact with the circle as well at the same time, with the parameter of the value are P1. So let's see some simulation, because as we will see, for the first model of interaction, we have the formation of lane. For the second, the formation of bound, and we will try to understand why. So we carried out simulation on a rectangle with periodic boundary conditions, and we use the collision-free model, speed models, and it has three parameters: the desired speed, the maximal speed, the desired time gap for the interaction, and the size of the agent. We have so the two values for the parameters, P1 and P2. And we observe that the first model of heterogeneity tend to describe lane when one of these three parameters are significantly different. So when the difference between the two values of the parameters is high enough, regardless of the parameters, it occurs for the desired speed, for the time gap, and for the length of the agent. We will see some simulation where we play with the time gap parameter. So we have here the system with a periodic boundary condition and the two types of agents, so here squares and triangle. And the first model of heterogeneity, and here we play with the time gap for the agent in gray, the time gap is 1 second, so it is a quite small time gap, and for the agent in yellow, the time gap is 4 seconds, so it is a bigger time gap. And what we will see quite fast, and this is a little bit what we already observed for the counterflow experiment, we will have stationary as a formation of lane in the moving longitudinal to the moving direction. And the system is stationary, so like this with this lane. Now, when we play with the second model, so here, as we will see, when an agent interacts in front with an agent of the same type, the value of the parameter are gray, so there's a 1 second per time gap, for example, them. When it interacts with an agent with another type, here's a triangle with a square, the value is yellow for the time gap, so 4 seconds. It is also everywhere like this. And what we will see quite fast is that this heterogeneity model will tends to describe the formation of bound perpendicular to the moving direction. So you can try this simulation online. Everything is online, so you can also download the code. So what we try to do now is Multicolor simulation to try to quantify and to observe when do we observe this fast transition to the lane and bound patterns. So we simulated the systems for different So with the random initial position, we repeated the simulation and we took average value. And what we measured is the mean speed of the agent and also the order parameter quantifying the lane formation or the band formation. So in these parameters, with this order parameters, we have an indicator between 0 and 1 for the lane formation and the band formation. And so it counts the number of pedestrians with the same type into lane or into bands. And we know that the value of the parameter is when the value of the order parameter is close to 1, then the system describes bound lane, and when the parameter is close to 0, then the system is disorder 1 or with that particular structures. And we played with the time gap parameter and also with the desired speed. So we increased successively the value of these two parameters into the models. So here, just to again explain the lane and bound parameters, and when the system describes lanes, then the parameter for the lane formation is close to 1, the parameter for the formation of bound is close to 0, and inversely, when the system tends to describe bound, then the lane order parameter is close to 0 and the bound order parameter is close to 1. We observe here the mean result of this Multicolor simulation, where we progressively increase the heterogeneity between the two families of parameter settings. So at the beginning, when the heterogeneity index is 0, all the agents are the same, so we have no heterogeneity. And progressively, we increase the different value of the time gap for the two parameter settings. And we see that there exists a critical heterogeneity values where we observe the lane and bound formation. So we observe here the lane order parameter abruptly goes to 1 when the heterogeneity exceeds this critical threshold here for the model 1, for the static heterogeneity model. And for the dynamic heterogeneity model, here we observe the formation of bound, and again, we have a critical value of the heterogeneity. And then we can observe that the speed of the agent are different for the lane formation because the lanes for each lane has a different speed. For the bound formation, it is not the case because they are moving in the bound are moving also in the moving direction. We carried out other simulation according to the waiting time, the simulation time, and we can observe that the bound and lane patterns appears quite fast already during the first minute of simulation, and it remains stationary after this time. And finally, we also had a noise into the dynamics to observe what appears when we perturb a little bit the dynamics. And for the lane formation, so the first model, we see quite fast that the noise tends to destroy the lane. This is a well-known effect, freezing by heating effect. So increasing the noise into the dynamic will reduce the formation of lane. And for the formation of bound, interestingly, we observe that the noise can, at the beginning, improve the bound formation. So this is clearly not a freezing by heating effect, but more an ordering by noising effect. At the beginning, so the noise makes that the lane appears for a smaller heterogeneity index. And when the noise is too high, then we see that the bounds tends to disappear. So to summarize the results, so we have identified two heterogeneity mechanisms from two species traffic flow. So the static heterogeneity model in the adjacent characteristics, and the dynamic heterogeneity model where the heterogeneity plays a role into the interaction. This is a kind of universal mechanism because we observe lane and bound regardless of the parameters we tested. And we also obtained similar results by using the collision-free first-order model or the social force model by Helbing, and both describe lane and bound formation according to the two heterogeneity model, M1 and M2. The work perspectives will be to analyze different kind of geometries, notably corridors or bottleneck, and to observe segregation effects for slower or bigger agents, and we have already some preliminary results in this direction. Especially when we consider bottleneck, we observe that the faster agents move into the bottleneck, the bigger are a little bit excluded of the dynamics. We also aim to analyze a little bit more rigorously the fast transition analytically, and we plan to develop a discrete lattice model, lattice representation of the two heterogeneity models, and then to analyze the fast transition by means of linear instability phenomenon and macroscopically to mean field solutions. And so this is what we plan to do, to develop into the next months. So many thanks for your attention.